Okay, right before Christmas, we talked about interference, okay, which is what happens when two waves try to occupy the same space at the same time. And we said that there were two kinds of interference. Constructive interference, where the two waves are meeting and they're in phase and the amplitude increases, or destructive interference, where the waves are opposite or out of phase and the amplitude of the waves decreases. Okay? Today, what we're going to be going over is what happens when a wave goes from one medium to another. Okay? We call it wave behavior at a boundary. Okay? The boundary would be the place where medium 1 meets medium 2. All right? Now, just as a quick review, what property of a wave can never change? Frequency. Right. Frequency can never change. That means that when a wave goes from one medium to another, its speed is going to change. The medium controls the speed of the waves. So, if the frequency is going to stay the same, and we know that those three things affect each other, okay, where V equals F times lambda, if this number can't change, if V changes, what does lambda have to do? Also change in the same way? In exactly the same way. Okay? If the speed gets cut in half, then the wavelength gets cut in half. The ratio between V and lambda cannot change because the ratio between V and lambda is frequency. Okay, everybody with me there? All right, so when a wave enters a new medium or goes from one medium to another, it's going to change its speed and it's going to change its wavelength. Just like the waves we were talking about before the break. Okay, water waves, as they approach the shore, okay, they slow down and they get shorter. Okay, the front end of the wave slows down, the back end of the wave hasn't reached that spot yet, so it continues to go the same speed, okay, and the wave gets shorter. And if you recall, I showed you that we did that analogy with the speed limit changes out here. Okay? In the 100-kilometer-an-hour area, the cars are a certain distance apart and going 100 kilometers an hour, but when they enter the 60 area, they are now closer together, traveling 60, but the same number of cars pass me every second in both places. Okay? Same is true for waves. If a wave slows down, it has to get shorter. If a wave speeds up, it's got to get longer. Okay? And the reason for that is the front of the wave will enter the new medium before the back of the wave. And it'll run away from the back of the wave, stretching it out. Okay? Everybody all right with that? Okay. So, we're going to look at what happens when a wave enters a boundary or encounters a boundary between two media. Okay? More things than just speed and wavelength change. Okay? And understand that while many characteristics of a wave change, the frequency doesn't. We're up to what now? 50 times that I've said that? Okay? It's a lot. It's important for us to remember. Okay. So, waves can travel through lots of materials. Okay? What was the name for the material? Medium. Right. So they can travel through lots of different media. Okay? But it will do so at different speeds. The medium, the properties of the medium determine the speed of the wave. Okay? So when light passes from one medium to another, its speed changes, okay, and that speed change leads to a change in the direction the wave is traveling. If it comes in obliquely, okay, that means if it doesn't come in straight on. If it comes in straight on, its direction won't change. But if it comes in at an angle, its direction changes as well. Okay, you've probably seen that if you've ever shone a laser or a light of any kind into water. Okay, the light just appears to bend when it goes into the water. Right? And that's because part of the wave, like this, part of the wave encounters the slower medium before the other part. Okay? So you can see out here, the waves are longer than they are here. So this is the slower medium. So if it comes in at an angle, part of the wave slows down before the rest, and that will cause it to pull around in something we call refraction. Okay? If you've ever, looked at something under the water, is it where you see it? Right? It's in a different spot because the light's coming out and part of it's speeding up before the rest of it and it bends the other way. Okay? So all of that is refraction. It's actually something that stone cutters or jewelers take advantage of when they're cutting precious stones like diamonds. Okay? if you're cutting a diamond, let's say we're doing this kind of a cut. I believe it's called a princess cut. It's not very symmetrical. They cut it better than that, but I don't draw it as good. Okay, so what do you want a diamond to do? When you look at it, you want the diamond to sparkle and shine. Okay, that's the whole purpose. Well, raw diamonds don't sparkle and shine. Okay, they look a lot like quartz actually. They're just kind of a translucent stone. Okay, but when you cut them properly, they can sparkle a lot. Okay, and the reason that they do that is a stone cutter cuts them into a certain shape with a certain angle at the bottom of the stone. Okay, so if light comes in the top, it slows down, and as a result, it bends, and it hits the bottom, what we call facet or side of the stone. Okay, if this angle is cut correctly, it's cut at what we call the critical angle. And the critical angle is an angle that doesn't allow the light to get back out. Instead of going out, it'll bounce off. So that light will bounce off and it'll come over here. And it'll hit this and it'll bounce off. And it'll go back out the top. So any light that enters the stone comes out the top and makes the stone sparkle. Okay? Now, they sparkle in air. You stick the same diamond under water and look at it and it won't sparkle. Okay? Because water makes light slower than air. And then the difference between the water and the stone isn't as big, and the stone doesn't sparkle. Okay? So, this is actually what jewelers look at when they're trying to determine whether a stone is real or fake. Okay? If you get a cubic zirconia, don't do that. Okay? If you get a cubic zirconia, okay, it's made of zircon, which is a type of glass. Well, glass doesn't have the same, what we call refractive index. It doesn't slow light down as much as diamond does. So you have to cut it at a different angle. Okay? So the bottom of a diamond or the bottom of a cubic zirconia would have a greater angle than the diamond would. That's all the person looks at. Okay? A stone cutter can tell right away. They'll put on that little monocle and hold it up there and they'll know right away whether that thing is real or fake. Okay? So if she's worth it, put a ring on it, then you get the real one. Okay? I was smart enough to do that. Okay? But I know people who were not. They'll find out. And then you'll be in a lot of trouble. Okay? If they're worth it, then get the real thing. Okay? And if they're worth it, you want to spend your life with them anyway, so do it right. Okay? But yeah, you can tell, a stone cutter can tell right away a fake from a real one. Okay? What about have you heard of these ones they're doing now? They're made in a lab. Okay? Diamonds that are made in a lab. All right? They would be cut exactly the same as a real diamond. Okay? Because they're chemically identical. All right? The idea of making a diamond in a plasma chamber is that there's no, how do we put this? Human cost to that. Okay? The process of mining diamonds and the people involved in that are sometimes, let's say, less than scrupulous, and a lot of people suffer. So there's kind of a trend towards getting these artificially built or constructed diamonds, okay, because there isn't any blood involved, hence the term blood diamond. Okay, so these ones that are created, okay, don't have that human cost associated with them. Okay, and it's virtually impossible to tell the difference. Okay, they're chemically identical. All right, everybody with me there? Okay, so the medium that the light travels in controls the speed at which the light travels. Diamond is one of the slowest materials for light to travel. Okay. All right. All right, so wave energy that hits a boundary, okay, is going to do a couple of things. Some of it will bounce off. What do we call that? If a wave hits something and bounces off of it, we call it, starts with R? Reflection. Okay? And some of it will travel past the boundary. We call that transmission. It goes through. Okay? So part of the wave will be reflected, part of the wave will be transmitted. Okay? How much of each happens has to do with how similar the two media are. Okay? If I had a boundary between, let's say, air and diamond, I'm going to see a lot of reflection, okay, and probably less transmission. They're very different, okay? If I had, let's say, water that was 10 centimeters deep and water that was 11 centimeters deep, am I going to see very much difference? No, most of that's going to go right through because water and water are very similar and the depths were also very close, okay? So the more similar the two media are, the less, let's say, crucial the boundary is. Okay, if we're going from one medium that's very different to another that's very different, okay, then we're going to see a lot of transmission or reflection difference. Okay, now some things you'll have to remember, okay, about boundaries. If a wave goes from a more dense medium to a less dense medium, okay, then we will see the wave get longer, because the wave will go faster. Okay? Less dense means easier for the wave to travel. Okay? So that'll be a faster medium. Right? If we're going from less dense to more dense, okay, when it hits that, then the wave is going to shorten. Okay? So this one here going this way, when the front of this wave hits the boundary, the front of the wave slows down. The back of the wave is still in the old medium, so it's still traveling at the faster speed. So it squishes the wave, and the wave gets shorter. Okay? Everybody with me there? Here's how I'm going to test this on a test so that you know. Okay? I'll give you pictures before and after a wave encounters a boundary. And you're going to have to look at the properties of the wave as well as the properties of the reflected wave to tell me whether the wave went from a more dense medium to a less dense medium. Okay? Here's the other way you can tell. You look at the reflected wave. If it's the first situation where we're going from slow to fast, the reflected wave will be upright. That means it'll look the same as the wave that came in. There will be a reflection, but the reflection will come back the same. If we're going from less dense to more dense, so a more difficult transition, the reflected wave will be inverted. It'll be the opposite. So if a crest came in, a trough will come back. Okay? In the first situation, when the wave hits that boundary, it's going from dense to less dense, the crest comes in, you get a reflected crest. Okay? Sounds strange, but I'm going to show you what it looks like here. Okay? I'm going to need... Okay. So the determining factor here, okay, as to how much transmission occurs and how much reflection occurs is the similarity, okay, between the two media. If we're going from more dense, okay, if it reflects off a more dense medium, so going from less dense, fast, to more dense, slow, then our reflection will be inverted. That you need to know. Okay, if you don't have the notes package, that you need to know. I guarantee you there will be diagrams on the exam about that exactly. Okay, and then reflection from a less dense medium, so from going from something very dense where the wave is slow to something that is less dense where the wave will be faster, I won't get much reflection at all, and what reflection I get will actually be upright. Okay, once in a while you'll get a question like a worksheet or something like that that I didn't make up, and instead of the word upright, they'll use the word erect. I don't use that because people chuckle and then it's just, yeah, okay? Upright, okay, means it's the same as the one that came in. A crest came in, a crest got reflected, okay? Inverted means a crest came in, a trough got reflected, okay? But just in case you come across a worksheet question, I think I changed them all, but I might have missed one or two, okay? If it says the reflection is erect, it means upright, okay? All right. Okay, I want to show you a video here about. All right, let's say I want to do a bank shot in pool. Okay, I'm going to play pool before. Okay, is a bank shot hard?
No, I mean yes, yeah.
It can be if you don't know how to do it. Okay, after today, with a little practice, you'll all be able to do a bank shot. It's a trick. Okay, because all it is reflection. All right, so. What you have to imagine is that the bumper on the pool table, the edge of the pool table, is a mirror. Okay? It's going to cause reflection. So if I hit the ball against that, it's just going to bounce off. But there's this thing, physical law, called the law of reflection. And the law of reflection says that anytime reflection occurs, the angle of incidence is equal to the angle of reflection. Okay? Whenever something bounces off something else, okay, the angle of incidence and the angle of reflection are equal. If you've ever tried to reflect the sun into somebody's eyes with the face of your phone, okay, so you've got the sun shining on your phone and twisting your phone over to shine at somebody's eyes, okay. Military will use like signal mirrors. They'll have a little signal mirror and they'll like flash someone else in their platoon or whatever to signal that they're ready, okay. All you're doing is making sure that those angles match up, okay, or they always match up. You're just making sure you make the right angle so that it goes where you want it to go. Everyone kind of following what I mean there? Okay, so that means that doing a bank shot is actually not as hard as you think it is. Okay, so to make a bank shot, what you have to imagine is that there's a reflection of the ball a certain distance behind the bumper. Think about this. When you looked in the mirror this morning, how far behind the mirror was your reflection? The same distance that you were in front of it. Okay? So, if I want to hit this ball right here, okay, so if I want to hit this yellow ball right here, I just need to make sure to do one little thing. Okay? This is how far that ball is from the bumper. Everyone with me there? That means if the bumper was a mirror, the reflection of that ball would be there. All right? So all I have to do is draw a line from the ball to that point, and where that line crosses the bumper is where I need to shoot the ball. Now, obviously, you can't draw a line on the pool table. Okay? They generally frown on that. And people will accuse you of cheating, and they'll be right. It is kind of dirty pool. But some buddies and I found a way around it in university, okay? Because we were all physics people. Okay? What we would do is we would use this, but the guy not hitting would stand with his pool cue right in front of him like this, right in that spot. And then our buddy would just sight to the pool cue, and wherever that line hits the bumper is where he needs to hit the ball. So, provided we hadn't, become too intoxicated, we could generally, make those shots, especially if the people we were playing against were heavily intoxicated, because then they wouldn't be able to shoot very well. Okay? We only had one guy actually catch us doing it, and he was very upset. Yeah, punches were thrown. It was not pleasant. Okay. And yeah, I'm a lover, not a fighter, so it didn't end well. Okay, so it works though. It's simple physics. As long as nobody catches you and your partner doing this little thing where you just look like you're resting on the pool cue, you can hit bank shot after bank shot. Okay, so it's a simple thing, and it just uses a very simple physical law, the law of reflection. Okay, all right. I'm going to show you a little video on reflection. So the things we have to remember about reflection are as follows, okay? When a wave encounters a boundary, some of the wave energy will be reflected. Some of it will be transmitted, okay? If it's going to a more dense medium, then the wave will be reflected back upright or inverted. Okay, if you didn't write this down the first time, you better write it down now. When a wave travels from a less dense to more dense medium, the reflection will be inverted. If it goes from more dense to less dense, the reflection will be upright. Okay, so that's the first thing we have to know about reflection at a boundary. The second thing we need to know about reflection at the boundary is that how much reflection occurs is based on how similar or dissimilar the medium or the media are. Okay? If they're very similar, there will be very little reflection. Most of it will go through. Okay? If they're very different, then a lot of it will be reflected. Third thing we need to know about reflection, the law of reflection. The angle of incidence equals the angle of reflection. Incident means incoming waves. Okay? Reflected means outgoing waves. okay? If a wave, the wave's on the springs there, okay? Did they still obey the law of reflection? They did. They came in at 0 degrees and they went straight back at 0 degrees. Okay, their angle of incidence, their angle of effect, they went right back on each other. Okay, there was no way to really make that angle. Okay, it was one dimension. All right. Now, the transmitted wave energy. Some things we need to know about the transmitted energy. The transmitted wave is always upright. That means it's always the same as the incident wave. If the incident wave was a crest, the transmitted wave is a crest. If the incident wave was a trough, the transmitted wave is a trough. Okay? It's always upright. Going into a new medium doesn't change the transmitted wave, or at least its orientation. Okay? We know the frequency will remain the same. That can't change. That's controlled by the source. Okay? We know that the wavelength and the speed will change in response to each other. So if the wave travels slower, the wave will get shorter. If the wave travels faster, the wave will get longer. Okay? Can amplitude also change? It can, because the amplitude of the wave kind of represents the wave's energy. Okay? If a wave hits a boundary and there's a lot of reflection, what will happen to the amplitude of the transmitted wave? Okay, let's think about it diagrammatically here. Okay, I've got this wave, here's the boundary, okay, here's the second medium. It's going to be green. All right, so this wave is going this way. This is less dense, this is more dense. Dense. Okay, when this wave gets to the boundary, okay, is there going to be a lot of reflection? Yeah, there will be. It's going into a more dense medium. Let's say it's a lot more dense. All right, so it's going to be very hard for the wave to go in. So that means that a short while later, what I'm going to see is this. I'm going to see a reflected wave that is inverted. Okay? If that wave suddenly appears and there's a wave in the more dense medium, they all got their energy from this wave. Would you agree? So that means the amplitude of the wave going into the more dense medium has got to be less. Okay? A whole bunch of its energy is here, going backwards in the new medium, or the first medium. Okay? So what we would see is this. Okay? What do you notice about the, well, I didn't do a very good job of the length there, but, okay, is this wave not just slower, but also shorter in terms of length? Right? This one's quite long, this one's quite short, this one's very tall, this one's very short, okay? Because a lot of the energy is back in the reflected wave. Okay? Little things like that to consider, because on a test, I could show you a diagram very much like this, and then say, which medium is more dense, 1 or 2? Okay, and you'd have to look at that and go, okay, I have an inverted reflection, that means the second medium is more dense, and the transmitted wave is shorter and smaller. That also means that it went into a more dense medium. Okay, so those little things that you got to be able to figure out. Okay. All right, so that's all the stuff about transmission. Amplitude changes, there's no hard and fast rule on that, okay, but it can change, okay. Wavelength, okay, is going to change in response to velocity. Velocity will change because it's a different medium, okay. Frequency stays the same. Okay, terminology. Sometimes you'll hear the term wave ray, okay. A wave ray is just a line that we draw to represent a whole bunch of waves. Because to do what they've done here, okay, draw a whole bunch of waves, takes a long time. So instead of drawing all the waves, they sometimes just draw a single arrow to say, the waves are going this way. Okay? and they can use that. Use it a lot more in physics 30 than physics 20 anymore. Okay, but a wave ray just represents a wave. Okay, the normal line. For the video we watched, use the term normal. Normal is just a line drawn perpendicular to the boundary to measure the angles. That's how we know that the angle of incidence and the angle of reflection are equal. We draw a normal line there, the two sides will be equal. Okay, so if you hear the word normal, okay, it's just a line drawn perpendicular to the boundary. Okay, we talked about this already, the law of reflection, okay, angle of incidence equals the angle of reflection. So you can see here, okay, we've got our wave ray and our wave ray here. Those angles are equal. Okay, here, same thing. Okay, waves coming in, waves going out, angles are equal. Okay. All right, everybody good with transmission and reflection? Okay, this stuff is a bit of memorization. Okay, you have to go over these parts of your notes and just make sure you know those things. Okay. All right, next behavior is refraction. This is one that we can see pretty easily as well. Okay, refraction is another way to change the direction a wave travels. Okay, and you simply do that by making it go into a new medium or crossing a boundary. Okay, when you make it cross a boundary at an angle, part of the wave hits the new medium before the rest of it. Okay, that part of the wave will change speed before the other part of the wave does. All right, so let's just say I'm going to draw that normal line here. Okay, so there's my normal line. It's perpendicular to the boundary between the white medium and the blue medium. Okay, and I can see that the waves here, these are going to be my incident waves, are they longer than the waves in the blue medium? Like, are they further apart? Definitely. Okay, I mean, if I draw a line here, right, use a little purple line here. Okay, that's how far apart the waves are in that boundary, or in that medium, right? If I put that here, those waves are shorter. All right, if the waves in the second medium are shorter, is the second medium faster or slower than the first? Slower, okay? Could ask you a question like that just with a diagram. All right, now, when the waves come in at an angle like this, obliquely, okay, and they slow down, okay, you can see here, these waves that are on the boundary, right, you can see that parts of them have slowed down and parts of them haven't. The ones that are still out in the fast medium are still going fast, but the parts of them that are in the slow medium go slow. And it's kind of like if you were walking along and you had your arm sticking out and there's a pole, like if you hit that pole with your arm stuck out, what happens to you? This part of you slows down, this part of you doesn't, and you turn. Okay? The waves are doing the same thing. Part of them is hitting something slower and it's pulling the other ones around because they're connected. Okay? So one part slows down and it turns the rest of the wave. We call that refraction. Okay? So the term for that is refraction. All right? That's why when you look into the water and see something, it isn't actually where you see it. Okay? If you've ever tried spear fishing, okay, it really becomes evident that that's the case. Okay? You can't aim for the fish with the spear and hope to get it. You actually have to push where the fish is not. And then when you look at your spear in the water, it's going to look bent. Okay? It'll look straight and then it'll hit the water and it'll look bent. Okay? Because of refraction. Okay? All right. When these waves come in, okay, they're going like this. Okay? But the waves that are in the new medium, okay, are going this direction. They bend towards the normal. That's going to be important in physics 30. It's not important here. Okay? But they bend towards the normal. What if I reverse this? What if this is medium 1 and this is medium 2? The waves are going out. Okay? So as they go into the fast medium, they speed up and they run away. Okay? Now they bend the other way. Okay? If that's my normal, my incoming waves were like this direction, but my outgoing waves are that direction. Okay? That's why if I'm looking at an object in the water, it looks like it's over here when it's actually there. It'll look shallower than it actually is. Okay. All right, I'll show you a couple of videos on refraction here. You'll learn more about this in Physics 30, like you actually do some math with this called Snell's Law. Okay. The thing with refraction is, okay, that's waves again traveling, traveling from one medium to another. Okay, all that happens is they change their speed and they change their direction, they change their wavelength, all those things we talked about. They all change because it's a boundary. Okay. All right. So this is kind of what we were looking at here. We saw these things in the video. Light going into water is going to bend this way because it's going to go slower in water. If I'm looking at a fish under the water, I'm going to see it much closer to the surface than it actually is because of that bending of the light. As it comes out of the water, it speeds up. It travels way faster in air than in water. Okay. Okay, and then from slow to fast, the opposite happens. We still get that bending though. It's just to see that the wavelength increases because the speed is increasing. Okay, you can see that here a little bit in this picture here on the right. Okay, you can see the waves coming in from the deep ocean. Okay, so they're traveling pretty fast, but there's this piece of land that's jutting out. The waves are going to slow down because of that change in depth. Look what happens to them over here. Do they kind of fan out? Okay, like over here on the far right, are these waves quite a bit further apart than the waves closer to the shore? Closer to the shore, they're traveling slower. Okay, these waves, this part of the wave out here stays in deep water. It goes fast, but it's connected to the part that slows down. That's creating refraction. It turns the wave. Same as what we saw in that big waves video about surfing. Okay, when it comes into that one spot, parts of the waves slow down and they get concentrated and they get really tall. Okay, same idea. Okay, now I can't remember if I got this one into your notes package or not. Is diffraction in there? Okay, so this one you'll need to write down, okay, for diffraction. So I'll give you a minute here to write down diffraction and kind of draw a diagram like these two diagrams here. Okay, don't worry about the pictures, just the diagrams. I'll give you a couple minutes and then we'll talk about it. So refraction, reflection, okay, all of that stuff, both waves and particles are capable of those behaviors. Okay, we're only talking about them from the perspective of waves, but both will do it. Diffraction is the one that only waves will show. We talked about Young's double slit experiment before Christmas. Okay? It was how he proved light was a wave. This is the one behavior of waves that particles cannot mimic. All right? So if I had, let's say I had a bunch of particles coming towards this narrow opening. Okay? If the particles don't get to that opening, they just bounce off the wall. Agreed? Right. So if it's particles headed towards this, then the particles that get through the opening just continue to travel in a straight line through the opening. Okay, they're particles after all. Whichever ones don't hit the opening are just going to go straight through it. Okay, and that's why people thought light was a particle for so long. This light appears to do this. Okay, if I leave that door open, okay, and shut off the lights in here, a beam of light comes in from the hallway. It's nice and straight. It doesn't diffract and fill up the whole room. Agreed? Okay, sound is clearly a wave. Sound does this. Okay, if I put my hands around my mouth, okay, then I make a narrower opening for the waves to go through, and they spread out better than they do if I'm just speaking. Right? So people knew sound was a wave. It clearly did this. They knew water waves did this. Okay, we can see it here in this aerial picture of waves going to the gap between these two rocks. We can clearly see they're far more circular on the other side of the rocks. They've diffracted. Okay? So if I'm talking about sound waves, and let's say that I'm at a concert and for some reason I bought a ticket that puts my seat right behind a big post. Okay, can I still hear the concert? I can't see the concert, Okay, that would be disappointing, but I could still hear it because the waves, the sound waves, will diffract. They'll hit that thing, they'll diffract around it, okay, and there'll be a gap there, but they'll diffract around that, and I'll still be able to hear them on the other side. If there's light on that side, will I be in the shadow? Yeah, again, another reason why people thought light was a particle, okay? It didn't appear to diffract. It actually does. But because light is so fast and has such an incredibly short wavelength, it doesn't diffract very much, okay? What determines how much diffraction occurs is the speed of the waves and the wavelength of the waves. The longer the wave is in contact with either the opening or the object it's diffracting around, the more it will diffract. So sound waves diffract a lot because they're long and slow. Okay? Light waves going through that opening are in contact with the opening for less than that amount of time. Okay? They get almost no time to interact with the opening, so they don't diffract very much. Right? They still diffract, but just not enough for us to notice. Okay? Everybody all right with that idea? Okay. So this is that one behavior of waves that only waves show that particles cannot. All right, now, does diffraction change the wavelength? Okay, these waves here, they're the same distance apart as these waves? Okay. Diffraction doesn't change the wavelength, doesn't change the speed, obviously doesn't change the frequency, okay? It just changes the shape of the wave. Okay? Diffraction doesn't change anything else. It's not moving into a new medium, okay? It's still traveling in the same medium, but it can change the shape. Okay? And it can change the direction the wave travels. So 3 behaviors of waves can change the direction the wave travels. Reflection, refraction, and diffraction. Okay? On your unit exam, you're going to need to be able to identify those behaviors of waves from a picture. Okay, so if I show you a diagram and say, what's that? Is that diffraction, refraction, reflection? Okay, now, I'm going to have you work on a few questions here that talk about interference from before Christmas, as well as the stuff we learned today, just to practice this stuff. Bottom of page 4, okay, and then on to page 5, there's some questions here about behavior of waves, all right, asking you to draw some pictures, some terribly drawn pictures by me, okay, some pictures I stole from other places, okay, for you to kind of interpret. Okay, there's some stuff about interference and there's some stuff about behavior at a boundary. Okay, so I want you working on those, and then we're going to go through all of them together as a class. Maybe today, probably tomorrow. We'll see how it goes. He's not sure. When he comes back. Okay, you have 9 days of class left. All right, your last unit exam is on the 15th. Okay. And then obviously your final exam is the last final, okay, January 24th at 9 a.m. All right, so make sure that you are here for that on time. Okay, we'll talk more about that as the time comes, okay, but you do have a unit exam next week, and you have your pendulum lab report, which I think pretty much everybody has done already, okay, and the simple harmonic motion assignment that lots of people are already done, okay, those are due this week. If anybody wants to hand in that simple harmonic motion assignment, I'll take it if you're done. Okay, I have a bunch that are marked, but okay, I'll take any if you want to hand them in early. Okay?
Can I see if I handed my simple harmonic motion?
You did.
If I handed mine in, you know I handed it.
Yes.
That's like the only thing I technically must work on. Anything related to school is literally just. The only reason I handed mine in today is because he said it's good and I should hand it in. If you need help, I can just,
We generally don't like to reschedule for things that are not like, you know, death in the family or something. Yeah, I mean, if we have to reschedule, we have to reschedule. Just know you won't write the same one as everybody else. Yeah.
Also, do you know anything about jury systems? Neither do I. I think it's electronic.
Is it an acronym?
No, maybe. That's just chaos.
But it's chaotic and it's hard to understand.
Yes, I can understand some parts of it. It's like interpreting the graphs and whatever like jury systems are.
Yeah, I can't say as I've ever heard of that term.
Okay.
Yeah.
I've never heard of it either. No, it shows an electrical diagram.
No, it's not.